All right. Hello, everyone, and welcome to the next session in our Rocky Worlds discussion series, where today we're welcoming Annelies Mortier from the University of Birmingham. And just before we get started, as a quick reminder of how we try and do things with Rocky Worlds discussions, when it comes to the Q&A at the end, please use your full name and keep muted throughout the talk. And at the end, when we do have questions, if you can, please put on your video and microphone and ask it in person so we can have a real discussion. Um, and with that, I will hand over to Annelies. Please feel free to start sharing whenever you're ready, and looking forward to hearing your talk.
Cool, thank you so much. So if you can hear the clock, I apologize. We have a clock tower on the campus here. Uh, um, so yeah, that's sharing perfectly. So hi, my name is Annelies Mortier. I work at University of Birmingham in the UK, and this is a fake background because it's currently raining, as per always in the UK, I would guess. So today I'm going to talk about small exoplanets and the hunt for an Earth twin. So I'm one of these Earth twin hunters, as I like to call myself. But spoiler alert, a lot of the presentation will be about stars. You got to sort of start with where we're coming from, right? So in this plot, you can see the total number of planets that we have discovered over the years versus the year of discovery. Now, the y-axis is logged, partly because we're astronomers and partly because that's how it nicely shows. The fact that it's linear in this plot means that exponentially we were finding more and more planets over the years, ever since we started finding them in 1992. So the doubling time was about 27 months till about 2015, and after that you can see that clearly it has slowed down. Now there's multiple reasons for that. Part of it is that we're using our resources to very much characterize in depth the known exoplanets. The part of it is also because it genuinely is getting harder to find new exoplanets. But having found 6,000 exoplanets, that is plain impressive, of course. Now, this plot is also mandatory. This is the family of exoplanets as extracted from the exoplanet archive. So here you see planet mass or minimum mass versus orbital period, and everything is in log scale. And in pinkish, you see the solar system planets. The different colors mean the discovery method, and here it's quite obvious that the transit and the radial velocity are the ones that are finding currently the bulk of the exoplanets. The other thing that is rather obvious is that there is a fair amount of structure in this, and you can probably give an entire seminar just on this plot alone, but let's not. You can also see that other than Jupiter, virtually all the solar system planets are very alone in this plot. Now, does that mean that the Earth or Mercury or Uranus are unique? Well, we'd love to think that, but we can actually not tell yet, because this is really where our detection limit is. The empty triangle on the bottom right is just our detection limit. Now, I'm here to convince you that you can only know your exoplanet if you know your host star, hence why part of this presentation is about stars rather than about planets. And this starts with the discovery methods, right? At the base of it, the two most used detection methods to date are radial velocities and transits. Both of them do not actually observe the planet at all. They are observing the star, and because of the effect that we see on stars, we infer the presence of a planet and its properties. So what we're really doing is observing stars, not planets. Now, I'm going to very quickly summarize what radial velocity and transit is. Radial velocity is the gravitational wobble because all planets in let's start that over. All objects in a planetary system are circling the center of mass, which is really close to your star, of course. When you find a planet through radial velocity, that's great. You can only actually get the properties through radial velocity if you also know the stellar mass, because otherwise everything is relative. The same with transits, where we get the radius of our planet. This is very simply what the geometry lines up, that you have a star, you have a planet going in between our telescope and the star, and you will see the light dip very easy. Now, you only have the radius of your planet if you have the radius of your star. So at a very base level of our detection methods, without knowing your star, you simply can't know your planet. And in that respect, I want to highlight two catalogs that I've been involved in. So one is called SweetCat, which stands for something, and it's basically a catalog of homogeneously derived stellar parameters for all stars that host planets. Now, we're listing every star that hosts planets, and there is a column saying whether or not we did the parameters, in which case the homogeneity is conserved. For radio velocity detected planet hosts, we're over 95% complete. For transit detected planet hosts, that's not true. Part of that is because most of the Kepler hosts are very, very faint. The other catalog that I want to highlight is the Great Stars catalog, which is basically a database of high-resolution spectroscopy, as well as the parameters for all bright dwarf stars in the sky, where our limiting magnitude is 8, hence the name Great Stars. This is being pioneered by the wonderful Alex Freckleton. She has a paper out explaining the spectroscopic method. She's doing the actual Great Stars release earlier this year, and is currently preparing a comparison method to check all the spectroscopic methods, because yes, there are still systematics in the stellar parameters that we give, and they're very crucial when it comes to planet parameters, of course. Now, the other question is then, if you know your star really well, is there a link between stars and planets? Because if there are strong links between stars and the kind of planets they form, if you are an Earth twin hunter, then you can very much narrow down the kind of star you should look at, if there is a clear link between what an Earth twin host would be. Now, back in the day when we didn't actually have small planets, and I was doing my PhD, there was this very strong correlation with the chemical composition of a star, which what we typically use call metallicity. Now, in the plot on the left, you can see the planet frequency, the relative frequency versus iron abundance, and this is just for giant planets. As said, there were very few small planets known at the time. Now, there's no denying that this thing goes up. Very clearly, the more metal-rich your star is, the more likely it is that you actually have a giant planet. Now, that is not true for small planets. Ever since Kepler, we found that out, that for small planets, their relationship is not starkly there. But it's not just about their presence, it's actually also about their properties. So if you look on the right, there's period on the y-axis and mass on the x-axis. So in the right part of the plot, you have all your giant planets. The red ones are the ones around iron poor hosts, and the blue ones around iron rich hosts. And you can clearly see that hot Jupiter close-in giant planets are very, very rare around iron poor hosts. And all the giant planets that we're finding around iron poor hosts tend to be much further out. So it's not just about them being there in the first place, but also their properties. Now, metallicity is, of course, a very complicated thing. The reason it's important for small planets and for possible Earth twins is that things like iron, magnesium, silicate are the building blocks of planets, of course. It's the building block of Earth, and it's the building blocks of most small planets that are out there. Now, if you think of these elements of stars in the Milky Way, so what you see here is the iron abundance on the x-axis, what we typically call metallicity, and the alpha overabundance on the y-axis. So alpha elements are things like magnesium, silicon, carbon, oxygen. So these are all the stars in the Milky Way in a density kind of fashion. So the sun would be at 0, 0, right in the middle of the bright blob. We're very ordinary as a star. But what you can see is if you go more metal poor, you also go more alpha enhanced. And what that means is that the balance of chemicals in the star, and thus the balance of chemicals in the environment where stars and planets formed, is wildly different than the sun. So everything that would be at 0 alpha overabundance has, from a balance perspective, the same elements as the sun. It just has less of all of them. Now, back in 2020, we studied one of these iron-poor alpha-enhanced stars, K2111, with one transiting exoplanet. So you see the transit on the right, you see the radial velocity curve all the way on the left, and there's a second non-transiting planet signal in the middle. The different colors are simply different instrumentation that we used. Basically what came out here is that the radius and mass that we found of this planet makes it consistent that the iron core has a mass fraction of about 10% in a 2-layer model. Now, if in case you don't know that, for the Earth, it's about 33%. So this is an iron core that's significantly less massive than the Earth. But that is entirely consistent with the fact that this star is iron poor and enhanced in alpha elements, which would make up the mantle of your planet. So then we would love to think, oh my God, there is a linear relationship between stars and planets. Now, people have been looking for this relationship for a while now. This is a plot that originally appeared in Adebekian et al. 2021. It's been adapted by Tom Wilson in order to put K2111b on it. They claimed a relationship, not one-to-one, but a relationship between stellar iron mass fraction on the x-axis, which is basically telling you something about the balance of chemicals in the stellar atmosphere, and then planetary density scaled with the Earth on the y-axis. Now, it is very obvious from this plot that there's maybe something there, but that the entire thing is skewed by the very, very few, and in their paper it really was only TOI 561b, which arguably is a really cool planet, very skewed by just these planets alone. So in order to study this properly, what is needed is that we have to find planet hosts of small planets that actually have these low stellar iron mass fractions. And then what you can do is use planet interior composition modeling to see what that planet might be made of. So here you see a cartoon of that made by Daisy Turner to just show what we think planets are made of in the most simple fashion ever, and geologists really don't like it. But you basically have an iron core, a silicate mantle, there can be some sort of icy layer, and then an atmosphere on top of that, possibly. And we boil our planets down to just that. Just as a reminder to all of you, whilst clearly the Earth has an atmosphere, it's why we're all breathing at the moment, and clearly the Earth has some form of water. From an exoplanet perspective, that is not really true. It is very, very tiny as compared to the mantle and the core. Now, what Daisy has done, this is Daisy, what Daisy has done is that she's looked for planet hosts of small planets across metallicity space, and this is showing her the stellar host of the sample that she's created now in that plot that we've seen before of alpha overabundance versus iron abundance. And as you can see, we're doing what we wanted to do. We have a whole bunch that are very similar to the sun, but then we have the ones here in the top where the balance of chemicals will be wildly different, and we have more than just two. So she went ahead and modeled everything. We have super Earths as well as sub-Neptunes, getting out the iron mass fraction of the planet, and then the stellar iron mass fraction by studying the spectra of the stars. And then we want to plot one against the other and hope for our linear relationship. Now, this is what she's finding. This is in prep, so it's not yet published, but we're working on the paper. The dots are the super Earths, and then the triangles below are the sub-Neptunes, and this is this planet iron mass fraction versus the stellar iron mass fraction. Now, I dare anyone to actually draw a straight line or a linear relationship through these points. Clearly, it is much more complicated than what we used to think from not having filled out the left-hand side of this plot or not having looked necessarily at sub-Neptunes before. So I want to point out that the errors here are larger than what you typically see in literature. That is because the ones in literature tend to be very underestimated. Model systematics or solar system abundances are typically not propagated. So these are the actual true errors that we have, making it even more complicated because they are rather large, but that is just the way it is. Now, HARPS Nord is the workhorse that's behind everything I do, essentially. And HARPS Nord is a high-resolution, high-stability spectrograph. It's at the TNG in La Palma. On the bottom left, you see a beautiful picture of La Palma. As long as the clouds stay below the telescope, we're perfectly happy. So this is an optical spectrograph with a resolving power of 115,000, which basically means I get lots and lots of spectral lines to play with. The thing that makes HARPS Nord and HARPS and Espresso and all these stabilized spectrographs so important for radio velocities is that they are long-term stable at a 1 meter per second or lower, 0.8 in our case, meter per second level. That is 1,000th of a pixel on the CCD, so that is impressive, and we are very, very grateful for the engineers that come up with this thing and build this thing so that we get to play with our beautiful spectra, essentially. Now, HARPS Nord has been observing since 2012, and with the HARPS Nord collaboration, we've focused for a very long time on trying to get masses accurate as well as precise for the small planets in the sky. So we're limiting ourselves typically to 4 Earth radii, which is half arbitrary, but 4 Earth radii is the radius of Neptune. So essentially what you're catching is literally all the sub-Neptunes and super-Earths. Now, this is radius versus mass for all the planets that had their mass characterized by radial velocities. So we're not putting TTVs on this plot. And everything that is in color is basically what the HARPS Nord collaboration contributed to the mass measurement. And then the white dots is from the rest of the people in the world. So we actually are doing a very good job, I might say. Now, this very good job needs a lot of references because there's an extraordinary amount of work trying to actually put dots on this plot. So I want to highlight everyone from the HARPS Nord collaboration who worked very hard in order to just put one, and sometimes in the case of a system, a couple points on this plot. Because in order to put a dot on this plot, you need extraordinary photometry in order to catch the transit of a small planet. You need extraordinary amount of radial velocities, but typically several of these have 100 plus radial velocity data points in order to get these kind of masses out. And on top of that, you also need a very good knowledge of your star, which arguably, if you're getting radial velocities, you obviously have entire stellar spectra that you can use to get intimate knowledge of your star as well. So it almost comes for free, between quotes, if you're getting radial velocity masses. Now, to just highlight what we're doing, if you just focus on wanting a radial velocity mass precision of 10%, which is necessary in most cases in order to distinguish between interior composition models. It's usually also necessary for the interpretation of atmospheres of the small planets, the actual very small planets. If you look for everything lower than Neptune, essentially the HARPS Nord collaboration has done 25% of all known small planets with a better radial velocity mass precision than 10%. When we go to the actual small planets, smaller than 2 Earth radii, the HARPS Nord collaboration has done 40% of those. So it really is a strength of us, and obviously our amazing spectrograph and the amount of time that we get to observe with it. Now, mass and radius and metallicity is not the full story. So these are the same planet sample. HARPS Nord collaboration are the squares, and non-HARPS Nord collaboration are the dots in planet density versus orbital period. You see that there's structure here as well, with some of the less dense close in missing. That is the Neptune desert that you see over here in this plot. But you also see that several of the super Earths start to drop off when you go to higher periods, because these signals are simply harder to find. The other thing is, if you're an Earth twin hunter, Earth has an orbital period of 365 days. That is off the plot easily. So we don't actually have precise planet densities for small planets currently above about 120, 140 days, so we almost have to double and triple that in order to actually find an Earth twin. So there's quite a challenge ahead of us. Now, and that brings me in the second part, where you really can only find your exoplanet if you know your host star. When you look at the radial velocity signals that have been detected over the years, so now we have the semi-amplitudes, which is the strength of your radial velocity signal in meters per second, versus time. Then you can see that in the beginning, we're talking for the 51 peg B, there was about 50 meters per second. And then after that, instrumentation got better, modeling got better, and you see us nicely pushing down. And ever since about 2008, we're somewhat stuck at what we call the 1 meter per second barrier. Now, occasionally planets are discovered with smaller semi-amplitudes or claimed smaller semi-amplitudes. The color is the significance of that semi-amplitude. So the darker the color, the more significant. So several of the very non-dark dots fall below the line. And some of the listed ones here are also still contested in the literature, whether it's actually a signal, yes or no. Now, our instruments are better than this. As I said, HARP-SNORT is stable at the 0.8 meter per second level. Espresso is stable at the 0.3 meter per second level. And there's multiple spectrographs by now in the world that are more stable than that 1 meter per second. So where are the planets? What we need is, of course, better instruments. It always serves to push the limits. As I said, Espresso now is pushing quite far. The KPF and HARPS-3 are also going to very much push the limits for that, and the instrumentation on the ELT as well. We need somewhat better observing strategies rather than go, oh, we'll give you 1 point here and then another point in a week. That's just not going to cut it in order to find an Earth twin. But again, that's something that can be worked on and is being worked on as we speak. What I want to focus on is that we also still need better data extraction. Again, you don't observe a radial velocity, you observe the star and its stellar spectrum, and you extract a radial velocity. And we need much, much better stellar knowledge. Now, just about the first one, with my team we've been working, and this was spearheaded by Florian Linhart, Dr. Florian now, and this is the multi-mask least square deconvolution technique. I always like to say that we're using LSD in order to get radial velocities. So this is a tailored radial velocity extraction method that works on a time series of spectra and uses a theoretical line mask based on the stellar parameters extracted from the spectra itself. So because it is so tailored and we're using in variety of different masks at the same time, that is why we typically do better than traditional techniques. So the cross-correlation function is typically what's being used to get your radial velocity out. It works really well, but it works on a spectrum by spectrum basis because it's something that runs on the spot in our pipelines. So it has to be and it works with generic masks because you can't possibly load in every possible star model on regular pipelines. Now, what you see here is the periodogram, so basically how strong a particular periodicity is versus period for Kepler-21. Now, Kepler-21 is a solar type but active star which has a small planet around it, Kepler-21b. Now, with the CCF radial velocities, the planet is indicated over here with the dashed line. You obviously did see the planet, but there were a whole host of other things going on as well, including the whole forest of signals around 17 days, which is the stellar rotation period of Kepler-21. Now, if we extract them more tailoredly with the MMLSD method, then what you can see is that the planet periodicity actually gets stronger, and part of the stellar rotation period and all the other peaks are reduced. So it does help and it does serve to just take greater care when you're just extracting your data in the first place. This is actually being worked on. It is available on GitHub, but my team here with Ben and Anna are basically working on getting an even better version out there for you all to play with, or you can send us your data and we'll do it for you. Now, the biggest problem is the star itself. I love stars, but when you're hunting for an Earth twin, or any small planet for that matter, the star does get in the way. Now, this is a beautiful picture of the previous magnetic cycle of the Sun, 2 cycles ago, of the Sun, where you can see from 1996 to 2006 that the star visibly gets different on the surface. It gets brighter, there's all these bright spots, there's dark spots, all kinds of things are going on. But if you think about it, if you're extracting radial velocities, what we're doing is looking at the velocity as governed by the light. Everything that's going on the surface of the star will contribute to that velocity in some form. Now, that would be fine if it would be stable. This clearly isn't stable. So what you end up with is a mess of different signals on different timescales, because you have the timescale of the full magnetic cycle, you have the timescale of the rotation period, you have the timescale of the oscillations, you have timescale of the convective cells changing about. So you have a whole host of different signals from the star, and just to put in perspective the kind of size we look at, we decided to actually observe the Sun as a star with our planet hunting spectrograph, because during the day HARPS Nord wasn't working because you can't see any stars other than the Sun. So we decided HARPS Nord's an instrument, it doesn't need to sleep. So basically we built a solar telescope. And you can see it on the left here, our solar telescope on La Palma. On the right is then the TNG looking at the moon rather than the Sun, which is quite nice. A picture just for scale. This is a solar telescope. It's totally huggable. It has its own little dome. It has its own little platform next to the big dome. I swear these are very regularly sized people. Now, we have been operational since July 2015, taking 5-minute exposures roughly from 9 a.m. Till about 4 p.m. It is telescope operator dependent when we stop. And so we have now a full decade of data, which has been released last month, including with a paper for all of you to play with if you want to. It's a lot of data, so think what you do before you start downloading it all. But this is our data. So because it is the Sun and the solar system, we know the solar system, you can subtract the solar system from the data, the known variations of the gravity of the Sun because of all the planets. So this is a data set of a star that genuinely does not have planetary signals in it. This is just the Sun being the Sun on a daily basis, and of course there's still instrument systematics in here, but I said HARPS Nord is stable at the 80 centimeters per second level. From the scale you can see here that this scatter is quite a bit more than that. Now, an Earth twin hunter like myself is looking for this. This is a sinusoid for those of you with small screens. So this is the blue signal with 9 centimeters per second amplitude. With a 1-year period. So if you are an Earth twin hunter looking for an Earth-like planet around a solar-type star in an Earth-like orbit, then what you're really looking for is in order to extract the blue signal from the black mass. That is why we're stuck a little. Now, I've been told that this plot is too scary, and arguably it probably is, but we can actually get rid of a lot of this scatter from everything we already know about stellar variability. Now, for one, if you were to zoom in, a lot of it is regulated with the stellar rotation period, the solar rotation period in this case. So these are periodogram-like plots. So imagine that you make a periodogram of a data set, and then you add a point to the data set, and you make a periodogram again, and again, and again, and again, and all over. Now, in this case, the x-axis is period, still in days. The y-axis is time from adding extra data points, and the color would be the strength of your periodicities. I took 6 different semesters, and essentially what you can see is that the periodicities get stronger and weaker over time depending when you're observing the sun, but it is very clearly in there. Now occasionally, if you focus on the bottom left, occasionally you see 2 solar rotation periods between quotes. That's obviously not true. This is in moments that there's very strong activity. You have so many spots on the surface that what you actually appear to see in the data is half the rotation period showing up. So one thing it shows is that yes, if you know your stellar rotation period, that will be visible in the data, you can do something with it, and then you can use red noise models to account for this variation and get a lot of the scatter that you saw before down. Now, another thing we've then done is most of the stellar variability that we know is governed in one way or another by the magnetic field of the sun. Now, SDO is the Solar Dynamics Observatory. It's a space satellite, and it looks at the sun in a resolved fashion. So what you see here is a plot from Federica Rastigno's paper, and on the left you see the continuum, and you see a little bit here bottom left, a group of spots that you can see. Now, if you then look at the magnetogram, so it also measures magnetic fields, then you can clearly see that the regions that were associated with spots are the regions with much higher and lower magnetic fields. If you look in the Dopplergram, where rotation has been taken off, you can see a much more complicated pattern as well, and again highlighting that several things are happening extra where you actually have these spots. Now, people have been working really hard to go from this resolved sun back to an unresolved sun, because for stars, we can't resolve those, and then created a radial velocity time series over the full magnetic cycle. And this is what you see on the top from the work from Raphael Haywood. And this is throughout the magnetic cycle, going from minimum to maximum and then back to minimum, that the radial velocities give variations up to 10 to 12 meters per second. And again, an Earth Wind Hunter is looking for 9 centimeters. So we're talking multiple orders of magnitude. On the bottom is the unsigned magnetic flux as measured by the SDO, and you see the exact same pattern. These correlate extraordinarily well. Then the question becomes, okay, cool, can we get this unsigned magnetic flux simultaneous with our radial velocity? So can we get it from the same spectrum, a measurement of the unsigned magnetic flux? Now, that was Florent's second project, still using LSD, and this time we included the theoretical knowledge of the Zeeman effect on certain spectral lines, where theoretically it's known how they would react to certain magnetic fields. Now, he used the solar spectra that we have and extracted what we call delta alpha b squared, which is our proxy for the unsigned magnetic flux. Now here you see part of the time series that he's done with his proxy in orange, and in purpley blue, the unsigned magnetic flux from SDO, and you can see that it matches extraordinarily well. And so we have now a technique to get this unsigned magnetic flux directly from arguably not very active stars simultaneously with a very stable radial velocity in order for us to actually see what is happening magnetically on your star. This is also on GitHub. It's also still actively being developed by Ben Lakeland, so that we can provide the best possible, and we are working on a paper applying it to other stars rather than the sun. Now, this was the unsigned magnetic flux, but signed magnetic flux also still holds a lot of information, and this was work done by Federica Rastigno, where now you can see that same radial velocity time series, but we actually had more data at the time, because multiple extra years had passed. So you see the onset of the next magnetic cycle here on the right, and on the top you see that signed magnetic flux. Now, clearly, there's not a one-to-one relationship anymore, because if nothing else, the radial velocities go up and then down, whereas the sign magnetic flux scatters around zero. But if you look at the periodicities hiding in that sign magnetic flux, and you see that on the bottom, then the rotation period of the sun, the second harmonic and the third harmonic are detected really cleanly. So signed magnetic flux still holds a lot of information with regards to your star very cleanly, so that you can apply the prior knowledge from this on the models that you're using to model your radial velocities. We figured that was an opportunity because we're not done with the HARPSes. There was HARP South in Chile, then there are HARPS North in La Palma, and La Palma is getting another HARPS. It's called HARPS 3 this time. So as far as I'm aware, they're currently literally assembling it on the mountain. So all the material has arrived on the mountain and they're building it up there. So we're very close to first light. Now, on the one hand, we have data from SDO. The polarimetry from SDO that gives us the magnetic flux comes from only one spectral line. Plus SDO still observes the sun resolvedly, and we do have to make some form of assumption in order to go from resolved to unresolved. Now, if you were to use HARPS 3, you could technically get polarimetry from the full optical spectrum, the same spectrum where your radial velocity will come from too, in order to see how every spectral line that contributes to the radial velocity behaves under the influence of a magnetic field. So we're building another solar telescope. So the solar telescope is called Aboras, after an old solar deity of La Palma called Abora. So whilst the acronym is completely contorted, there is a meaning for it. So Aboras will be a polarizing solar telescope. So the mountain itself, because of HARPS North and HARPS 3 being on the same mountain, HARPS North has the sun as a star telescope just looking in regular intensity light, and Aboras will look in polarized light, and then we can use the same data at the same time. Now, this is being built by Ben Lakeland on the left and Kieran, who just joined the team a couple months ago, on the right. So Aboras will do circular polarimetry, so it's getting that signed magnetic flux. This is just to show that this is entirely possible with the HARPSes. So HARP South has a polarimeter, and this is work done by Nikolai Piskunov, where on the left you can see the V-Stokes magnetic profiles throughout rotation of a particular star, and from that you can get the signed magnetic flux on the left, where you see very nice variation across the rotation of the star. Now, the point being here is the errors. So this was done with the HARPS polarimeter. The HARPS 3 polarimeter arguably should be an order of magnitude better than the HARPS spectrograph. So the small size of these errors is what we would need in order to study solar-like stars, and clearly what is possible if you're using a HARPS-like spectrograph. Now, this is roughly the design. The design has changed a bit over time, but we're essentially going to have a pinhole with a UV protector because we don't want to fry our instrumentation, and then a rotating quarter wave plate that then will split the light into two integrating spheres, so that we are sure that the light is scrambled really well and that we lose all information on local things on the sun, that we really do go to an unresolved star, and then everything gets fed into two fibers that then travel on their way to the HARPS 3 spectrograph. So in conclusion, I hope I convinced you that it's very important to know your star in order to know your planet, but also in order to find your planet. And it is especially important for the small planets whose signals are considerably smaller than the stellar variability signal. The HARPS North is a workhorse, continues to be a workhorse for these small planets. And stellar activity continues to keep us in a job, essentially. We're using the sun as our case study, but new techniques using LSD and new instrumentation using polarimetry are the way forward in order to finally find that Earth twin. And if you find enough of them, you can also actually put them in context of all other small planets. Thank you.
All right. Thank you so much, Annelies. That was a really interesting talk. Um, so we now open the floors to questions. If anyone does have any questions for our speaker, please raise your hand and I'll call you forward. And when you do come to ask your question, if you could pop on your video as well, that'd be fantastic. We have a question from Rob. Go ahead.
Yes, thanks. So thank you, Annelies. It was an excellent presentation, very interesting. And can you show the plot from Birmingham 2021? And this paper was really focused on trying to identify a population of super Mercuries. And but later on, they kind of went back on this conclusion where they think in a paper from last year, they said, well, maybe we haven't really found a super Mercury population.
Yeah.
So do you think that the new HARPS instruments can maybe also help reduce these uncertainties enough that we can more conclusively say we do or we do not have observed super Mercuries?
Yes, it's a very good point. This here is what they claimed were super Mercuries. It's a very hard claim to make, of course, with a limited sample that you have and without our ability to actually go there and drill and see what it looks like. New instrumentation will definitely help on the y-axis, of course, because getting these errors down in planet density is important. Getting these errors down is very, very hard. As you can see, the ones that we can do with 10% precision, which still is on this plot, actually the visible error, needs an extraordinary amount of data, of course. The other thing that you need is simply more. We simply need more small planets in order to figure this out, because there is, to some degree, an enormous selection and human bias in these planet demographics. Part of that is if you start observing a planet host in order to get the mass, where the ones that would be heavier than you would expect, you will find faster because the signal is larger. People will also select certain targets in order to do follow-up because it needs to be feasible. So the biases are very hard to control in contrast with transits. The x-axis is actually also still a really big problem. The errors here are underestimated with at least 50%. Part of that is model systematics of stellar atmospheric models that are still a thing. You do have to take that into account, and that is not always properly taken into account, partly because we don't necessarily know what these model systematics are. And the other part is that you do need to use the solar abundances in order to make stellar iron mass fraction, and solar abundances simply also have errors on them that were not taken into, they were taken as constant for this plot, for this paper. So there's a lot of work to be done, but at the end of the day, what it means is we need to fill it more, not just with planets, but being assured that we are doing it across this x-axis scale in order to find everything. Having done that, we can clearly show that it gets filled here as well. The super Mercuries would be on top of here. They're gone right now. So yeah, it's a hard struggle, but this is just not enough data yet. No.
All right, thank you very much.
Okay, any other questions? I guess I have a kind of a broad one. So you showed the solar variability and as a function of the periodicity, and then pointed out that there was some spot activity, and that was almost as in this plot showed like almost as strong an influence on the observable here. I was curious about extrapolating this to other stars, and are there like additional known unknowns about other stars that may have intrinsic properties that might affect this and add additional noise in that spectrum that we need to get that noise down?
Yeah, this is we use this technique on other stars all the time, like for like a decade now. So getting this rotation period of a star, if it has some form of spots on it, through photometry you can get the stellar rotation period quite well. But even in the radial velocities, it gets quite obvious quite quickly, depending on the level of activity of a star. So this has successfully been used on multiple stars in order to tease out the planets. The most impressive ones, arguably, are young stars, where this technique is employed on young stars where the stellar variability signal, because of rotation, we're talking hundreds of meters per second now, but by employing the techniques, knowing what that rotation period is, they do get out the masses of, for example, AU, McB, and others, where the radial velocity is extremely dominated by a rotation period. Now, we had a whole period of the sun at minimum, where the sun wasn't really spotty at all, and yet our scatter, as you can see, is still considerate. So this is not because of spots, because there weren't any spots at the time. So there is a whole host of, indeed, as you say, unknowns, even from the sun, that we're not entirely sure what the physics is behind it in order for us to actually inform the models that we're using. One big thing is granulation. So basically the convection cells on the surface of small mass stars. And one thing is supergranulation. So granulation is somewhat of a known, especially in the solar community, and we're getting somewhat of a handle on that, slowly but surely. Supergranulation is an effect that even solar physicists don't completely understand, and is still seemingly larger from what we can tell than an Earth twin signal. So there are several unknowns, and that is why we're using the sun, hoping to extrapolate, but truth be told, you will be able to extrapolate this to solar type stars, as in FGK probably, because it's very much related to how the surface reacts. Extrapolating to M dwarfs will probably be a no-no, because their stellar variability is simply very different. Extrapolating to subgiants and giants, again, probably not, because again, their variability and the way the star works is just very different. But if you're biased like me and you work on solar type stars, then this is great.
So just a quick follow-up. So is there a correlation with this noise with the iron fraction within solar-like stars? Would you be able to anticipate more noise in different ends of the iron fraction window?
Yes, so we do see effects with wavelength, for example. So the redder part of the spectrum and the bluer part of the spectrum are somewhat differently affected. That is a technique that has successfully been used to I'm sorry, to kill planets back in the day. So planets that were claimed back in the day from optical radial velocities were then observed with an infrared spectrograph, and the signals wasn't there. And it was completely different, showing that whatever was seen couldn't possibly be created by a planet, because the planet would be stable across wavelength. So we do use that, the fact that it changes from line to line. The problem is, in order to have our very small errors on radial velocities that you also still need all the lines and all the information in order to get that very low photo noise error. So you can't just, a typical spectral line of a solar type star is about 7 kilometers per second wide, and we need to extract that with 1 meter per second precision. So you do need the thousands of lines at the same time, and you can't just cherry pick.
All right, thank you.
We
have
a question in the chat, and also for those watching on the YouTube live stream, if you post any questions in the chat on YouTube, I'll also repeat about that. But the question is from Lynn, who's not able to turn on the camera. She says, "Great talk, Annelies, thank you." And she has a tongue-in-cheek question for you. If you had infinite funding, what kind of spectrograph would you build?
Oh God, no! If only, right? If I had infinite funding, I would definitely go for ever slightly higher resolving power. And so the route that Espresso has taken, if we can get 200,000 resolving power, now visibly looking at the spectrum, that will look exactly the same as 115,000 resolving power spectrum. However, we would downsample the lines much more, and all the small changes in spectral lines would be much easier to characterize if you simply have higher resolving power. Now that comes with a whole host of issues, of course, because if you have higher resolving power, you split your light over even more wavelengths, so you have to be really careful about the kind of size of telescope you then put that on, etc., etc. But hey, I'm getting infinite funding apparently. But I would not build one spectrograph. I would build multiple spectrographs across the globe, so you can track your star for, like, not forever, but yeah, you can track your star without the day-night gap, that you can track your star just with a much denser cadence.
Cool.
All right, any more questions for Annelies?
I have one really small question, more of like a clarification. On the plot that you showed on slide 12, I was kind of wondering what exactly is on the y-axis there, because it says yeah, over here, the right plot. So it says the iron fraction of the planets, but this is in mass fraction, which for the Earth would only be 32%, right?
Yeah, so this is stellar iron mass fraction on the x-axis, and on the y, you're asking about the y-axis. No, yeah.
The y-axis, yeah.
Yeah, this is planet iron mass fraction. So the reason that that is higher than the 30% that I mentioned before is because you have iron mixed in the mantle from the iron oxides as well. And iron is considerably heavier than the oxides. So we modeled the Earth with the same modeling code, which was using Planetic. And the Earth itself comes out, the Earth would light over here. So it's partly because it's all the iron in the core as well as all the iron that is mixed in with the oxides in the mantle.
But the Earth's mantle only has 8% of iron oxides. The other 92%
Yes,
is other oxides.
we figured that out this morning. I did not change my slides. No.
We have another question in the chat from Victor. For your ideal spectrograph network, is there a limitation on mirror size required for the EPRV work to make exo-Earth detections around FG dwarfs?
That is it's a very interesting question. Now, in principle, we don't necessarily at the moment need to go bigger per se, because as shown by Alex Freckleton in the Great Stars catalog, we have, I think the number is 3,000 something, the bright dwarf stars brighter than 8. So as long as we can focus on bright stars, we're perfectly happy with like a 2 to 4 meter size mirror, for which it has been proven that these spectrograph designs work really well. There's a sweet spot around 2 to 4 meter to make the spectrograph designs as we're building them very efficient. Now, obviously, once you want to start going to slightly fainter stars, and inherently most transit hosts will be fainter, then you will have to go bigger in size on your mirror, but that will probably require a different design than a HARPS-like design. You would have to redesign the way the spectrograph works. So for HARPS-like spectrographs, between 2 and 4 meters is the sweet spot. And there's 3,000 bright stars, so you have some time.
All right. I had another question about the plot on slide 12.
Oh, here we go. I think Daisy is online, if you...
So I just noticed when this came up again, the error bars. I was curious
large.
if there's like a trend in the error bars in any direction as you kind of move up the y-axis or across the
So
x-axis? For instance, if you have a larger iron core, if that adds more uncertainties on how big a hydrosphere might be, for instance.
Yeah, it's a good question. So the sub-Neptunes are the ones that are most problematic here, actually. So the super Earths are relative. If you look at the posteriors, they're relatively well constrained from their prior, where we came from, the prior information we gave. The errors are just still relatively large. The sub-Neptunes, there's definitely a trend in there because they're much less well constrained currently. There's a lot of model degeneracies when it comes down to sub-Neptunes. I think as a community, we're still trying to figure out whatever these things are. So the model assumptions behind the Planetic code, which is using the biceps model created in Bern, is basically behind this, but that doesn't say that that's the ground truth for sub-Neptunes, or that we're any closer. But yeah, so that's where it comes from. We simply aren't constraining it as well as we do super Earths, but even for super Earths, it is still really hard. That is where it will help if we get our mass error down. But jumping from 20% mass to 10% mass is an enormous effort, and going from 10% to even less than that, we're talking at this point, we're talking thousands of data points that you would need in order to do that effort. But yes, Lynn is giving me infinite funding, so then we can do that.
All right, thank you. Any more questions? Going once, going twice, 3 times. Oh. All right, well, I guess with that, we shall thank Annelies again for a really interesting talk. And that's it for this Rocky Worlds discussion. We're not going to be doing one in January, partly because, it's the holidays and people will still be getting back into it, and also because the in-person Rocky Worlds meeting will be happening this January, of course. So the discussions will be back on February the 5th, where we're going to have the next talk from Moa Person. So thanks everyone for joining. Thank you, Annelies, for your talk, and hope to see you all next time.
All right, cool.
Thank you,